Hello, welcome back as we continue our journeys in geometry concepts. Today we're going to look at non-Euclidean geometry concepts, just briefly touching upon some very basics of some other types of geometry other than plane geometry that you learn in high school. We're not going to get anywhere in depth with these. And then in the next video we'll get into something called fractal geometry. So we're looking at some different types of geometry you may or may not have been exposed to before. Typically, you're not in high school. Alright, so what is non-Euclidean geometry? Well, Euclidean geometry is that geometry you typically do study in high school, focuses on what's happening on planes. Or even when you get into three-dimensional objects, those objects still, the faces and things still have characteristics based on existing on certain planes. And a key building block in developing this geometry is a postulate or an axiom. You probably learned a lot of those when you took high school geometry. These are just statements that you come right out and accept as true. And then as you go on, you realize that there's some statements that are not postulates or axioms that, like theorems, where, okay, we have to prove it's true before we can use it and everything. But a postulate or axiom is something that you just accept it as true and move on. It's like the foundations. And particularly, Euclidean is named for Euclid. He was known to be the one, who wrote the elements that set up the Euclidean geometry. But his fifth axiom, also known as the parallel postulate, helped, when people were looking at that, it helped lead to discoveries about non-Euclidean geometries. All right, so what is this fifth axiom, or Euclidean parallel postulate? Okay, it says given a line and a point not on the line, one and only one line can be drawn through the given point parallel to the given line. Okay, so what does this mean? Let's say we have a line. I'm going to draw it in a different color. We'll draw it like this. And I'll just call this like L for line. Often you'll use a cursive L. And let's say we have another point out there. We'll call this point P. P for point. This postulate is saying there's only one line that can be drawn through P that's parallel to L. So let's call that line maybe M or something. So we're wanting to make sure that L, line L, is parallel to line M. If you try to draw any other lines other than line M through point P, no matter what you draw, it's not going to be parallel to L. So that line M, that is the one and only line that can be drawn through point P parallel to the initial line L. And this is dealing with planar geometry. This is assuming a flat plane, which you can visualize like being like a flat sheet of paper that goes on and on forever. Except a plane doesn't have any thickness, so paper is just a physical representation of this concept. But anyhow, so that's what the Euclidean parallel postulate states. And by exploring this, some discoveries were made about what happens when you're on other surfaces. Because, let's get real, the real world does not exist entirely on a plane. You can use planar geometry to model certain things happening on flat surfaces and so forth, but we live on a oblate spheroid, so pretty close enough to a sphere to kind of right now just estimate and say we live on a ball. It's like a ball that's squished a little bit, or if you look at the shape of the universe is not flat. The universe is not a sphere. It is more like a trumpet horn with two of those like put together. I'll draw it in a second. So some of these principles in Euclidean geometry just don't work on those surfaces. And that's how your non-Euclidean geometries were born. Start looking at, well, what does work? And this parallel postulate is what helped them to start looking at it. Okay, so yeah, these geometries came about, and they explain behaviors in both realistic and hypothetical settings. And I listed some realistic, like thinking about the Earth as a sphere, thinking about space as kind of that trumpet horn shape, or it's also called a pseudosphere. So hyperbolic geometry deals with that pseudosphere or trumpet shape. Spherical geometry is also called elliptical geometry, or Riemannian, named for Riemann. So those definitions are not necessarily the same. All right, so like with Euclid's, the fifth postulate there. All right, let's say you're dealing with spherical geometry or elliptical geometry. You're dealing with a big ball. Okay. So on that ball, if you want to think about lines on the ball, your lines are actually great circles. Like if you looked at the equator on Earth, or if you looked at a circle that goes through the North Pole and the South Pole, lines are called great circles. So examples would include like the equator on Earth. If you had a ball in your hands and you wanted to put a piece of ribbon around the ball, if you wanted that ribbon to kind of lay flat and go all the way around the ball and make as big of a circle as possible while laying flat on the ball, it would go around one of these great circles. As soon as you try to draw, like look at another circle that's not a great circle, like let's say you try to look at this one. This is not a great circle. If you tried to put your ribbon on that circle, it wouldn't lay flat. It would always have a little bit of it'd be kind of half on the ball and half off. And so those aren't considered lines. So those lines, they cover like the widest or fattest part of the ball when you're trying to make a circle. And your ribbon would lay flat if you're doing it. And as far as if you think about like from an ant's perspective, they look like lines. If you start crawling around on one of these great circles, it looks straight and flat. And if you didn't know any better, if the ball's big enough, like the Earth, you keep going, you feel like you're going around forever and ever. Like there's no end to go infinitely in opposite directions. It's straight, and that's pretty much it. And like a line, a great circle technically has no thickness, but you know, we have to represent it by drawing something that has thickness. So with the spherical geometry, as soon as you start trying to draw, as soon as you start trying to play with Euclid's, with that fifth postulate there, as soon as you start trying to do the fifth axiom of geometry on it, you might have this great circle here in the equator. And as soon as you pick a point somewhere else on the ball, you're not able to draw any great circle through that won't intersect the other great circle. So we can't draw what's called a line in elliptical geometry, or a great circle parallel to the existing green one. That goes through that point. It's not possible. So on elliptical geometry, that fifth axiom doesn't work. It's saying, given a line and a point not on the line, no line can be drawn through the given point parallel to the given line. So it can't draw a line or great circle parallel to the existing green one that goes through the point. So it breaks down like that. When you get to your other kind, your hyperbolic geometry, that shape's really weird to look at. Hyperbolic geometry is something called a pseudosphere. It looks a lot like two trumpet horns that are put together like this. And it's thought that space has this kind of shape. You know, the space and everything, think about it as like this big rubber sheet. And as soon as you have gravity on a planet or something, it bends this rubber sheet. So you start having this warped kind of shape. All right, so on this pseudosphere, if you want to start drawing lines, you could have a line like that goes like this. You could have a line that goes like this. You could have a line that goes like this. So there's all kinds of ways you can draw your lines on this thing. As soon as you start trying to talk about the whole fifth axiom there, you might have this given point, and then let's say this purple one's your given line. You can actually draw multiple lines through that point that never intersect your given line. So let's say the purple one is your given line, and let's say that green point is your given point, or black point, sorry. The black point's your given point. Notice that the green and the blue both are parallel to the purple. They are lines that exist on this shape, on this pseudosphere, and they will never touch or cross that given purple line there. So you actually have, so given a line and a point not on the line, two or more lines may be drawn. Through the given point parallel. parallel to that given line. So this was really mind-blowing for some of the early people who were stumbling upon these, well, not stumbling, but coming up with these discoveries as they were trying to explore this fifth postulate. For some people, it's like, well, to them, Euclidean geometry was the one and only geometry. So they just felt like this can't possibly exist. What is my mind doing here creating this? It doesn't make sense. But that foundation was still being created, even if they didn't think it could be possible or real. And thankfully, that foundation survived at some point, because then people down the road, like Einstein, were able to use these geometries to help them think about space and what's happening. Who were some of those people? So some key players early on in this non-Euclidean geometry included Saccari, a Jesuit priest in Italy. He worked on hyperbolic geometry, 1667 to 1733, during his life. He didn't live very long, but I guess he lived long enough, but anywho. The work came about while trying to prove that the fifth postulate wasn't needed. He was trying to look at Euclidean geometry and say, maybe we don't even need that postulate as one of the foundations or postulates in Euclidean geometry. Maybe we can throw that one out. He was trying to, whittle things down and see if they could get it compressed more. And he had faith that Euclidean geometry was a true geometry. So when he made this discoveries, he tossed out his work and was like, there's no way. And so he didn't end up receiving credit right away for founding non-Euclidean geometry. A little further down the road, he was in 1667 to 1733. In 1823, nearly 90 years after Saccari died, Hungarian Bolyai pursued his own ideas and also developed hyperbolic geometry. He had declared, I have created a new universe from nothing. Unfortunately, when he made it known or public that he had done this, the German Carl Friedrich Gauss had said, oh, I already beat you to it. I just didn't publish because I was hoping for posthumous or after-death recognition. I'm not sure the point of that, but I'm sure he had his reasons. So that was kind of devastating for Bolyai. I didn't find that out. At the same time that Bolyai was working, there was a Russian named Lobachevsky who independently had nothing to do with Bolyai or Gauss up here. And he developed the same ideas and published a paper around the same time. So keep in mind, this is before people wrote letters and were in touch with people in other parts of the world, but this was before our instantaneous internet and those kinds of communications. So, they had no idea anybody else was working on these things. He ended up writing several books and received great recognition for his work. So that's quite a bit going on there. And as far as our elliptical or Riemannian geometry, it's named for Bernhard Riemann. He was a student of Gauss. Gauss had worked and not published his work on hyperbolic geometry. Well, when we got to the elliptical or spherical geometry, one of his students suggested it in 1854. So we're looking at 1823 was Gauss and Bolyai, and then like a little over 30 years later was Riemann. All right, and as mentioned earlier, this hyperbolic geometry explores things on the surface of a pseudosphere. You can look at triangles too on it. We looked at the fifth postulate, but you can also look at triangles. Interestingly, in hyperbolic geometry, a triangle it adds up to less than 180 degrees versus planar geometry where it's 180. Einstein thought that a particle in space would travel in a path the shape of a geodesic, the shortest and least curved arc between 2 points on a surface. He was thinking about this pseudosphere as he thought this. But his work included exposure to Riemann's writings as well. So really Einstein's thoughts ended up combining both spherical and hyperbolic geometry, or hyperbolic and like all of these ideas. hyperbolic and elliptical. All right, so for hyperbolic, well, remember on a plane we draw a triangle on a flat surface, and let's say we have angles A, B, and C. We say that the measure of angle A plus the measure of angle B plus the measure of angle C is 180 degrees. So that's just, basic Euclidean geometry. But as soon as you try to draw a triangle on the pseudosphere, it's a different kind of scenario. On the pseudosphere, you draw a triangle, it's going to look like this. So again, imagine drawing this triangle on the end of a trumpet bell. You're not going to be able to draw straight edges. And your angles, when you look at them, are not going to be able to add up to 180 degrees. In fact, the angles add up to less than 180 degrees. So that's the reality in hyperbolic geometry. All kinds of stuff going on there. With spherical geometry, if you're exploring that on a ball, on that one, the angles can add up to more than 180 degrees. I say we briefly discuss this in class with a homemade model. Well, for now, you're going to have to settle with me drawing a model because we're not in class and I'm not going to turn the camera on myself. But let's say we have, a big ball. We have our great circles. There's a couple different ways that you can think about drawing a triangle on this. Like, if you look at the North Pole, like you can draw the edges of a triangle have to be drawn on the great circles. But let's say that you could do it to where when you draw it, it comes down like this. It uses pieces of some great circles. And when the great circles meet another the great circle here at the equator, you can have two 90-degree angles in your triangle. So the angles in a triangle on a sphere add up to more than 180 degrees. And remember, if it's hard to imagine those being 90-degree angles, imagine yourself being an ant. Little ant standing there on the equator, and this other great circle drops down in front of you. To you, it's going to look like this nice, straight, 90-degree angle. Now, the third angle up there at the top doesn't have to necessarily be 90 degrees. It can be less than 90 degrees. But you could also draw one that is 90 degrees too. So you could have a triangle on a sphere with 270 degrees. That's pretty wild to think about when we're so trained about these triangles being... So you could have a right angle up there. And you could end up with 3 right angles. So you could end up with 270 degrees. Isn't that wild? But these are the very things that gave some of the early founders angst. They're like, how is this true? How can this be possible? Euclidean geometry is the way to go. This doesn't make sense. But it really did make sense. It's just different surfaces. All right. Just wanted to kind of briefly wrap this up. This part I already mentioned about how shape of space, you can think about how like Earth having gravity bends space. so that around Earth it's not the same shape. So you end up having to deal with hyperbolic geometry when you're considering things traveling, like spacecraft traveling in space. One other example that your book mentions about these kinds of geometry, what is another real world example? There's a little blurb in the current textbook that talks about medical researchers and mathematicians working together. You know how like trying to draw the map of the world on a flat surface can be a pain? Well, they're trying to map the brain, which is a 3D object, onto a 2D map. And they're able to use these various kinds of geometry to help them do this. It's complex, because think about the shape of a brain. Brain has a strange shape. There's all kinds of little fissures and whatever else, and bulges, and nobody's brain looks exactly the same. So they're trying to make sure they get the depths and get everything to look correct in the flat image. So they use topology, which is something we're going to talk about in the near future. They have to use hyperbolic geometry, elliptical geometry. And that's how they're accomplishing this kind of medical research. So this stuff's being used, even if you don't use it in your everyday life, you may be feeling the impacts of it. So if you ever need a brain scan, you're hoping that they're getting the conformal mappings correct. Because you want them to be able to figure out, do you have a tumor or something? And then if you're, whatever it is you're trying to figure out, and when they look at the surgeons and others look at the maps, you want them to know exactly where things are located. So it's important to, if you're going to cut into somebody's brain, you want to know exactly where you're going. So you need this mapping to be precise and accurate. So you can take mathematics for that, geometry, if you ever have any issues where you need any kind of scans in your body, trying to map 3D onto 2D. All right. Okay, so thank you for joining us on this. I look forward to chatting next about fractals, fractal geometry. You have a project related to that. I love fractals. In fact, my master's degree thesis had to do with fractals. So this is like my all-time favorite section of this course. We're only going to briefly touch on it. My thesis ended up being an 85-page paper. We're not going to talk about it, but I'm just going to give you like the first day introduction to what fractals are. So those are fun. So I look forward to seeing you again. Thank you.